Hey, let's do a little activity about activity, right? Um, these are three quantities, right? So we can talk about n, and n is literally the number of undecayed nuclei. So this is going to be a giant number, like 10 to the 23rd would 6 times 10 to the 23rd is like a mole of these, right? Okay. Then there's something called lambda, which is the pure per second probability of a particular nuclei decaying. Okay, and it has the units of probability per second, right? So it's the probability per second. That's why it's seconds to the -1, right? And then there's something called activity, okay, which if we had a Geiger counter that could detect every single decay somehow, right? It would be the rate at which it would be the number of beeps per second. It's the number of decays per second. Now, here is the relationship that we're really going to focus on, okay? And then we'll talk about this in another video, right? And then this is just, all this says is that the activity, right? The activity is basically the negative, the derivative, the time derivative of the number of nuclei, right? Basically, it's how many nuclei you're losing every second is what this means. I hardly ever use this formula, but that's just a definition of activity, right? Let me give you an example, though, of this formula. Let's suppose your lambda is 0.2. Okay? What that means is that a particular nuclei has a 1 in 5 chance of decaying every second. Okay? Doesn't mean in 5 seconds it will definitely decay. It's just saying that it rolls a 5-sided dice. If it comes up with a 1 on the top, maybe, right, then it decays that second, right? It could go a long time without decaying, but that's the probability, right? Let's suppose we have 100 nuclei, okay? Well, this formula here predicts that the activity in the first second is going to be 0.2, right, times 100, right? That we'll get about 20 decays, right? Does that make sense? We'll have 20 decays per second for the first second. And then, of course, herein lies the rub. After that point, you've got 80 nuclei left, and so the activity will be 2/10 of 80, and then after that it'll be somewhat less, and that's why it is this this exponential decay I'm sort of foreshadowing, right? Okay, but this is the basic idea: is that if every nucleus out of 100 nucleus has a 0.2 chance of decaying, then you're going to have 20 decays, right? Now that is, you could get 18, 19, 16, 12, 11. You could have 25. You could have more or less than this if you had 100 nuclei, right? Statistically, it would vary, just like if you rolled dice or something like that, right? But if you had 100 moles of it, right? If you had that many atoms, 10 to the 30th or something like that, right? Atoms or whatever, right? Then this would be exactly 20% of the atoms would decay. So once you get into the huge numbers, this works out to an exact probability, right? So let me do an example problem here, okay? And this one's going to be ugly, right? So here is our activity, okay? That's how many decays per second, okay? And so ultimately, I'm going to say activity is equal to lambda n, right? And since I know the activity and I know lambda, I can figure out n, right? Okay, so that's my first step, is n is equal to the activity divided by lambda, right? Okay, so that's going to be 8.249 E16, right? And this is decays per second, right? That's supposed to be a per second, right? Okay, divided by the probability, which is very small, 2.098. It's like 2 parts in a million or something like that, right? E minus 6 per second, right? Okay, and this is going to be literally the number of atoms that we've got, right? Okay, so 8.249 E16. By the way, what kind of detector could detect that many counts per second, right? And the answer to that is that none could really, but there are statistical ways with a detector and the geometry to figure out that even though you're only detecting a portion of them, a partial. Okay. Okay, so this number I get 3.9318. There are ways to know that if you're detecting only a portion of the decays, like you got a sample here and you've got a little thing here detecting it, right? You know how efficient this is, and you know what part of the solid angle all the way around this that subtends, and you can figure out the tremendous decay rate like that. Okay, and this is times 10 to the 22nd. This is atoms, right? And then the question is, how many moles is that? Well, let's figure that out, right? 1 mole would be this many, right? So the formula I'm using here is moles equals number you have divided by avocado's number, right? Okay. So I'm going over avocado's number. I got to divide everything by avocado's number. Okay, 6.02 e to the 23rd, right? And this is atoms per mole. And now we can figure out moles. So I'm going to divide by, and I get 0.06531 moles, right? And now I'm going to use this relationship. Moles also equals grams divided by grams per mole, right? Right? Yeah. So therefore, grams equals n times grams per mole, right? Okay. So I'm going to multiply this guy. I'm going to go 0.06531, right? And then this is the atomic mass, right? So that's the molar mass of this thing, right? I just rounded it. We know it even better than that because it's a particular nucleus, right? But we don't need any more precision than that, right? So I'm going to multiply by 222.02. And I get that it's 14.5007. And then how many do we have? We got four sig figs, so I guess we could say 14.50 grams. Yeah. And since we're in chemistry land, notice that we do get grams, right? Yay. Okay. So these are things you definitely want to know this, right? You're definitely going to want to know that, you're also going to want to know this, a little bit of chemistry here, right? Okay. For this kind of stuff, right? Because we're getting into basically nuclear chemistry. Well, it's physics, really.